Yeah, good evening.
Good evening, sir.
Good evening.
Okay. Thank you for agreeing for us to meet today. Oh, sorry. Hello, are you there? Okay. Yeah. Okay. Okay. Can you hear me?
Yes, we can. We can.
Yes, sir.
Okay. So I wanted to get the slide up. I don't know. If you see the slide, you let me know. Okay, so that yes.
Okay.
Let me broadcast. Yeah. Do you see the slide, please?
Yes, sir.
Yes, we see it.
Okay.
Yes,
Thank you
yes.
very much. Welcome once again. Sorry about yesterday. Today we will begin our course work and look at introduction to structured program design. Right. Okay. So what I want you to do is just to confirm that you have the requisite material. Are you able to access the LMS?
Yes, sir.
Yes.
Yeah.
Yes, sir.
Okay, and you are on the page. Everybody's on the page.
Yes.
Okay,
I am
that's
on it.
good.
Not yet.
That's good.
Not yet.
No
Oh,
problem.
please, I will post the material on the LMS, and then we will get to the LMS and then download or do the assignment or the work. So kindly try as much as possible to get onto the LMS, okay? It's very important. Contact the people who are need contacting so that you can get onto the LMS, okay?
Okay, sir.
Okay, thank you very much. Okay, so let's quickly go through our objectives or our course outline for today. Today, we will look at an introduction to computers and programming languages very shortly. Then from there, we will discuss what are the origins of computers.
It's muted.
Pardon? Hello? Hello?
Yes, sir.
Yeah, someone was saying something.
You can continue, sir.
Oh, okay.
Please go on.
Okay.
Please
Then
go
we
on.
will. Okay, thank you.
Yeah.
Then we'll also look at a brief history of programming languages. Then we will also talk about computer systems and what they contain, because we want to program computers, and so you have to understand what makes up a computer. Okay. Then we will also look at programs and software. So the software we are going to write, we need to understand what it is all about and how it is written. And then those who write, or the process of writing, we call that programming. So we'll look at computer programming, and then we'll look at various types of programming languages. And then we will quickly look at types of language translators. So today, this is the itinerary we have for the lecture. At any point in time, if you want to ask a question, kindly put up your hand. I'll try as much as possible from over here to get connected so that we can hear your question and then respond to you appropriately. Okay. You can also use the chat tool to type your question if it's not too long, and then we can also respond from there as well. Okay. So the word computer is a word we know mostly now, okay? But computers, the name or the term computer, it has been used over the years to represent the okay, to represent the science of computing or calculating. Okay, so when we say to compute, we simply are saying to calculate. Now, to calculate, what are we calculating? We are calculating some mathematical values or some proposed answer to maybe an algebraic expression or something of the sort. Okay, so any tool that enables us to do this calculation can or is what we term as a computer. Okay, so a computer is mechanical or an electronic device which accepts some input, processes this input based on stored instruction, and then produces an output, or can store this output or this information for future reference. Okay, so you can see that mostly people believe that computers are only electronic, but computer can be mechanical as well. Are you with me? Okay, so a computer can be mechanical as well. It's not only electronic, but it can be mechanical as well. Okay. Now, so based on this example or based on this, we can see that there are several examples of computer systems. Okay, so our traditional understanding of computers, I think most of you already have used a personal computer before, okay? And then most of you already have a laptop, okay? Oh, sorry, it's not coming up clearly. Let me change the marker, okay? So most of you already have a laptop. Some of you have tablets, okay? Some of you have maybe a gaming machine. Some of you have a smartwatch. Okay, so smartwatches also, what do they do? There's some program on them, and then they collect some information from the user. Maybe they collect your heartbeat, they collect something from the user, and then they process this information in using some program, and then they produce some output. That information too can be stored on them as well, okay? Then what people tend to be confused all the time or tend to not agree is that because computers are used for computation, so what it also means is that we can have the abacus. The abacus is a typical example of a computer. I don't know if most of you have seen a device like that we use in maybe in the nursery school with some metal railings and then some pebbles strung around the metal railings that the kids use to count. So this is also a computer because it doesn't have to be electronic. Okay, it can be mechanical as well. Okay, then even sticks down, across, that kind of thing. It's called a tally system. Okay, so this kind of counting is also regarded as a computer. Okay, now what is most important, whether it is electronic or mechanical, is that computers work based on some stored instructions. Computers work based on some stored instructions. So with the abacus, we know that the instruction is that when you move a pebble across, it's an addition. When you move a pebble back to its original position, it's a subtraction. Okay, so there's a program at play. Then also with any of our modern day computers like the smartwatch, okay, or maybe a mobile phone, right? There's some instruction that tells the user or that picks some information from the user or picks some information from the network and then uses that instruction to manipulate the information and produce some output. This instruction is called a computer program. Okay, most of you are used to maybe another term for computer program we refer to as apps. Okay, most of you are used to this term apps. Okay, apps is short for application. Okay, so an application or a software or a program are all synonymous, and what they are is that they are just sequence of instructions that tell the computer what to do specifically. Okay, now they can be grouped, or computers can be grouped into different groups based on the type of computer they are, right? The generation, or based on the type. Okay, so we have maybe the 0th generation of computers. Okay, the 0th generation of computers. Okay, while at the beginning of computing, how computers started. Okay, when there was no electricity. Okay, that's what we call the 0th generation. Okay, then when there was electricity and there was electronics, okay, we also had what? The 1st generation. Okay, so computers like the Pascaline, okay, computers like the analytical engine, computers which like the Leibniz loom. These are all examples of 1st generation computers. Okay, they use something called vacuum tubes. And then we can also classify computers based on their usage. Okay, so we term that as type. Okay, we have what? Supercomputers, we have personal computers, we have mainframe computers. All of that stuff is good to know. Okay, I'm just mentioning it over here, but I'm sure you have a course which will introduce you to computers proper, and where that discussion will be had. Our course focuses solely on programming using structured program design. So I'm going to just walk around that just to give you general knowledge, and then we are going to veer back into the programming. Okay. Now, moving forward, we want to talk about a brief history of computers. Okay, so computing began long before electricity or electronics was even discovered or was invented. Okay, because we were calculating. Okay, whenever we are doing any calculation, we regard such an activity or action as a computer. Okay, so pre-electricity era all the way to the 1800s or 1800s, we had tools like the abacus that I was talking about. Okay, so the abacus is a very old tool used by the Greeks, even used by the Chinese long before, and then sent to the West, and then used by the Greeks, used by several civilizations to do the Polynesians and all of them. Sorry, the Europeans, early Europeans, used this tool to do computation. Okay, but in Africa here and in different parts of the world, we also have tools like sticks, stones, calories, and different items that we use to do counting. Whenever we are doing counting, we are doing computing. Okay, now somewhere in the 1800s, thereabout, people or different scientists began to build different tools to test or to help people to do counting. Okay, so one of those notable examples is Blaise Pascal, French mathematician and scientist, who built what we call the Pascaline calculator. Okay, so it doesn't look like anything like you are imagining it looks like. You can Google it. Okay, it looks pretty much like a wooden box with a copper frame and some dials and knobs. And what this calculator was is that this calculator was a mechanical calculator. Okay, so by being a mechanical calculator, what it means is that it doesn't have any electronics, but it has wedges and hinges and screws and all those things. And then once you turn a lever, it moves some wheels inside the device around. Okay, and then somewhere after that, this German scientist also built something called the stepped reckoner. Okay, and then this Englishman is world famous for building what appears to be a first mechanical demonstration of what computers really could be. Okay, he's called Charles Babbage. He worked with another engineer or scientist called Ada Lovelace. Okay, so we'll talk about Ada Lovelace also very soon. Now, his invention was called the analytical engine. Though it was not finished, it proved some key concepts in programming. Okay, now around somewhere in the 1896, this American businessman, okay, or who you come to in the future refer to as Herman or Hillard Herman, right, during the counting or a census, built a machine called the tabulating machine. It's a mechanical machine. It does tabulation for the American Statistical Agency or Service. Okay, so they used it to count the number of Americans by the 1896 thereabouts. Okay, so it was also a mechanical device, no electrical components, but it was built to do counting. Okay, then fast forward in 1930s thereabouts, Vannevar Bush led a team to develop what we call the differential analyzer. It uses the same idea from Charles Babbage's analytical engine, but by the 1930s, electricity had already come up and electronics was a booming industry. But they used something called vacuum tubes, okay? So vacuum tubes. It's an unreliable technology, okay, but it was what they had then. Like today, maybe we have fast computers and we think that our computers are fast. In the near 50 or 100 years, they will have faster computers and they will think that we are rather archaic, or we were rather archaic, okay? So the 1930s also saw the development of the Z1, Z2, and the Z3 computers during the first I think during the Second World War thereabout. And then Hewlett Akins and his team built a machine called the Mach-1. So the Mach-1 was a machine that could perform large-scale calculations involving numbers. Okay. Now, a breakthrough came in 1946 when a machine called the electronic numerical integrator and computer. Okay, for short, the initials forms a term we refer to as ENIAC. Okay, so ENIAC was one of the first general purpose electronic computers that was developed. Okay, and from there we had the UNIVAC, we had the EDVAC, and so many other models of this same computer. Okay. Now, what led to the various changes within this period was that, like I said earlier, they were using vacuum tubes, but around the 1956 or 1963 thereabouts, the technology improved so that we had what we call transistors. Now, they switched from vacuum tubes to transistors because transistors are much more reliable. In fact, today, if you are seeing anything on your computer, it's because of that technology. It's called transistors. Okay, you can do a lot with that idea. Okay, it's a technology. Okay, and so because transistors were much more reliable, the computers that they developed over the years became much more how do I put it? Became much more accurate, and they were not going off or not computing wrongly. Okay. Now, later on, they managed to put 2 or 3 or 4 or more of transistors together to form something called an integrated circuit. So integrated circuit is also referred to for short as IC. Now, a transistor just contains one switch, one electronic switch. Okay, transistors contain one electronic switch, but an IC can contain 100 or more electronic switches. Okay, now with the ability to put about 100 transistors into one component, they started building ICs. Okay, and then somebody thought of, okay, let's do large scale let's do very large scale integrated circuits. Okay, VLICs. And then somebody said that, okay, let's increase the number to VLLICs. And so we've kept on increasing the number of transistors. The more transistors they add, the smaller your computers get. Okay, so your computers have decreased in size because of the technology called IC or transistors. Okay, transistors have made your computers smaller and smaller and smaller, so we can fit more in one. Okay, now in around somewhere in the 1971, we moved from building large computers which could fill a whole room to building simple, small scale computers which could do all the processing, but also they were able to divide the computer processing into components. Okay, so one of the key components was a component called the microprocessor. Okay, so or more commonly we call it the CPU. So you put the control unit and you put the control unit and the ALU, right, arithmetic logic unit, into the same processor. Okay, and that's what we call the microprocessor. Okay, and now companies like Apple came into the market, and companies like IBM and Dell, and then all those other companies started coming in. Okay, so this is a brief history. Though there are lots of things I am not mentioning here, I hope that you can remember that all of these things are important, and more. Okay, and more of them as well exist and are important for your for you to grasp the entire idea of the programming. Okay, now where did programming also start? Did we just create computers and then programming began? No. Okay, the computers they were creating then didn't have that idea that let's create a computer and then let's create a programming language and then put the programming language to write programs for the computer. The computers they were creating then, like the ENIAC, like the EDVAC, like the UNIVAC, and all those ones, they were built to do one thing and one thing. For example, if they built a machine to do salaries, that machine can only do salaries. You can't install anything on it. There's nothing like installation, because they built that machine with salaries in mind. So the software and the hardware, there was no divide between software and hardware. The machine did salaries and that's it. You give it numbers and people's names, it can do salaries. Okay, so the idea was then. And then somebody came up with the idea that let's divide the computer so that there will be software and hardware, so that once you build one machine and you want to do any operation, you can just write the software and put it on that same one machine, and it can do those operations you want. Okay, so from the very beginning, we had people like Ada Lovelace, okay, writes the first algorithms, which we consider as the first program for the analytical engine. Okay, so Ada Lovelace is a key figure in programming. Okay, then Konrad Zuse also built a programming language. This is in German. I don't know if there's any German speaker here who can pronounce that word, but I can't pronounce that word, so I'll leave it be so that I have not. I'll leave it as it is. Okay. Then we built assembly language programming. Okay. Remember, as at this point, programming was just done as zeros and ones. Okay. Programming was done as zero. So if you wanted to write any instruction for the computer, you had to learn how to communicate in zeros and ones. Remember, human beings don't talk in zeros and ones. We talk in words, in sentences, in phrases. And so people had to be trained to speak in zeros and ones, or to write programs in zeros and ones and feed it to the computer. And then when the computer also returns answers in zeros and ones, they will translate those answers for the users. Okay. Now, because that was hard, they came up with assembly languages. So assembly language is a mnemonic programming language they developed around the 1949 to help make it easier for human beings to communicate with the computer using normal words. Okay, even though they don't look like normal words, right? But it is somewhat normal. It is better than learning zeros and ones. Okay, then the first programming languages came somewhere around 1957, and here the first ever programming language that was developed was called the formula translator, okay, or formula translation, or Fortran. Okay, so Fortran was designed for scientific and mathematical program. The scientists created this for their physics and their maths programming. Okay, so that's the simple thing about that as well. Now, what are the first programming languages? Okay, so we have Fortran, and then you often hear, I don't know how many of us have heard of Lisp. So Lisp is also AI programming language. Okay, it's used for logical programming. Okay, for predicate and first order logic, propositional logic programming. Okay, then we have a programming language called COBOL, which was designed somewhere in 1959, and this was usually for business applications, so business analytics, spreadsheets. It looks like a spreadsheet. Well, today you guys only call it Excel, okay, but it's actually spreadsheet. Okay, so it also looks like COBOL looks like that, but it's not actually a spreadsheet. It's a programming language as well. Okay, then we have languages like Algol and then Basic. They came around 1960s, and in 1972 we had the C programming language by Dennis Ritchie, and then in 1980 we had the object-oriented C++. Okay, then around that time in 1990 we had Python. Okay, so Java came later in 1995. JavaScript was after Java, and then today we have several programming languages that have been developed for different purpose. Each fits a different purpose. Okay, each one will fit a different purpose. We have languages like Ruby, we have languages like PHP, we have Kotlin, we have Swift, we have so many. We have R, we have F#, we have D, we have Lava, we have GameMaker, we have ML, we have Mathematica. There are so many programming languages. There are hundreds and hundreds of programming languages. Is there any question at this point? So we can address the questions. Yes. Is there any question at this point?
No, sir.
Okay. 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 Now it's important that before you program, okay, you understand what you're actually programming. Because we'll be programming computer systems, you need to understand the various components of a computer system. So when you pick any computer system at all, the key components of computer system are about 5 to 6. Okay, we have something called the central processing unit. Okay, and in that central processing unit, we have two key components, something called the ALU and something called the control unit, or CU. Then we have the main memory. Then we have the secondary storage or secondary memory. We have output devices and input devices. And what I will just say is that these days we always have some form of communication devices. Okay, these days we always have some communication as well. Okay, so communication is also very important to the computer system. Okay, now let's take the computer system or the various components and look at the components one by one. The first component we'll take a look at is the central processing unit, or we call it CPU for short. So the CPU is acting like the brain of the computer. Remember, any living being needs a brain or needs a way to think or process information. Okay, so the CPU has or contains the components for processing information. Okay, now there are two key components of the CPU. Okay, we have the first component called the arithmetic logic unit. The arithmetic logic unit stands for the ALU. Okay, so when you hear ALU, it simply refers to the arithmetic logic unit. Now, it's the part of the computer that processes all the computations. Okay, so when you are maybe doing an addition, you are doing a subtraction, you are watching a movie, you are saving a file, you are documenting, whatever it is you are doing, the computer sees it as a sequence of operations which needs to be carried out like mathematics. Okay, and so it uses the arithmetic logic units to carry out these computations. Now, the second key component you have in the CPU, okay, is the control unit. Now, you need to be able to control the computer, turning it off, turning it on, shutting this down, connecting this device, disconnecting the device, how the hard disk is moving, copying something, moving things around, checking whether the keyboard works, checking the screen, making sure that the color, all of those things are done by the control unit. So like the name suggests, it is a control part of the computer. Okay? Are we okay?
Yes, sir. Yes, sir.
Okay. Now, the second other key component, okay, is main memory. Okay, so when we say main memory, we are referring to the staging area of the computer. So, for example, when you go to work, usually you have your books and maybe files or stuff in a bag. Okay, but when you get to work and you sit at your desk, what you do is that you open the bag and then put the stuff you are going to work on your desk. So main memory is the staging area of the computer. That's where all the work is done. Okay? But the analogy also works this way, that when you are done working, you don't leave the books and the things on that desk. You most likely pick the books and things and put it into the bag again. Okay, so what that happens is that when the power is switched off from any computer, anything in the main memory or everything in the main memory is lost. That's why we call it volatile memory. Okay, because everything is lost. Okay, it is a workspace or the staging area. Very important. Everything is done over there. But the moment you turn off the computer, everything is gone. Okay, so you need a way to store that information permanently. So hence we go to the next component called the secondary storage. So secondary storage is where you store the information permanently. That place, when the power goes off, the information is not lost, it's still kept. So we have examples like CDs, we have floppy disk, we have hard disk, we have flash drive, like pen drive, what you call pen drive. We have solid state drives, we have optical drives, we have DVD, we have Blu-ray, magnetic tapes, cassettes, all of those things. When the power of the computer is switched off, your information is still there. Remember, your pen drive has hundreds of movies, but the moment you pull it out of the computer, the movies don't disappear. They are still there. When you plug it back into another computer, you can watch the same movies. Are we okay? Okay. Finally, but not the last thing, are the two other important components, the input devices and the output devices. Okay. So input devices allow you to enter some information into the computer, whilst the output devices are used to display or to hear. So examples of input devices, we have the keyboard, we have the light pen, we have the microphone. Currently, I'm talking into a microphone. That's why you can hear me from the other end of the call. Okay. We have the joystick, we have the scanner, we have a barcode reader, we have a trackpad, we have a touch pad, we have a webcam, we have the mouse, we have controllers, game controllers, keypad, whatever it is. So all of the kinds of devices that allow you to enter some information. Okay. Then we have devices that show you the information or that allow you to feel or to hear the information. So we have like something like what? A speaker. Speaker. You can hear something, you can hear the audio through a speaker. Okay. You can see the presentation from your screen, your monitor. Okay, whether it's a touch screen or not, you can see the information from there. You can print a hard copy of the slide. Okay, you can hold that hard copy. Okay, you can also use a headphones. Okay, headphones or earpods. These days we call them earpods. Okay, and those other ones. You can print a very large digital picture or photo. Okay, so all of those are examples of output devices. And I was saying lastly, these days we also have communication devices. These ones allow you to connect like Bluetooth, like Wi-Fi, like radio. Those kinds of things are examples of communication devices. Are we okay? Okay, so any questions for me? Or you guys are all sharp brains?
No, sir.
Okay, thank you. Okay, now let's go back into computer programming. Okay, so we said that a computer program can be referred to as an application or a software or a program. Okay, sometimes we refer to it as with any of those terms. Now, a program or software or any of those things is a sequence of instructions, okay, which specify how the computer will perform the operation. Okay, so for example, if I want to send a message from my phone to another phone, I need a special program that can be installed and that can send messages from my phone to another user's phone. Okay, that's why you have WhatsApp, so that you can send that information. So you can have WhatsApp, but if the other person does not have WhatsApp, you can't send them a WhatsApp message. Okay, so the WhatsApp program contains the special instructions that tell your phone how to send messages to the other person's phone. Do you understand? Okay, so the instructions are what we call a computer program. Now, computer programs are intangible. You cannot touch them, unfortunately. Not like software, not like hardware. The hardware you can touch. Okay, the computer itself, physically, you can touch it. You can touch your phone, but you can't touch the WhatsApp in the phone. Okay, so please take note of that. Now, it is the software that tells the computer how to perform the task. And the computer performs the task by running the application or the software. Okay, now there are two major classes of software. Like I said, because our program is not introduction to computers, I'll not go deep into them. But we have basically something called system software and application software. So system software is the software that coordinates and controls the computer. Okay, so we have software like the operating system, your Android OS or your iOS or your Windows 10 OS or your Windows 11 OS. They are responsible for helping you turn on your computer, turn it off, control the sound, control maybe the network. You can turn off data, you can turn on the Wi-Fi, you can share a file, all because Windows 10 or the Windows people built those things for you to do that kind of interaction. Okay, now those are not the only ones. Okay, so we have operating system, but we have something called utilities, and then we have something called device drivers. Okay, so device drivers, for example, if you install operating system and then you now realize that the sound is not working, you go to the website of the manufacturer of the machine and then download sound drivers. Okay, the driver is a small software that helps your hardware to communicate with the operating system. Okay, then we have application software. So application software is all the software that makes the user productive. or that helps your program to perform the task. So maybe I want to send a message. I don't need operating system to do that. I need special program that can send message. Okay? Or I want to record a lecture online. Okay? So I need to go and get maybe Zoom or Microsoft Teams or some other application, okay, that will do that specific recording of the lecture. So we have softwares like word processing software, we have spreadsheet software, and then we have photo editing softwares. Okay. Next, we now go and see that, okay, so with all of this, what we're trying to do is trying to learn programming. So what really is programming? Okay. What really, is programming. So programming is basically the process of what? Solving problems using programming languages. Okay. Now, there are different ways to solve the problem. We're going to learn about different techniques and different things as well. So over the coming weeks, we will talk about structured programming in detail and some of the things that we need to understand in order to be able to solve problems using specific programming languages. Okay. Now, there are 4 main classes of programming languages. We have machine languages, we have assembly languages, we have high-level programming languages, and then we have a class called scripting languages. Okay. Now, two major classes of these programming languages, machine languages and assembly languages, are also called low-level, okay, programming languages. Okay. These two major classes are also referred to as low-level programming languages. Okay. So assembly language and machine language are also called low-level programming languages. We have high-level, and then we have scripting languages. Okay. Now let's go and look at what machine languages are. Now, machine languages is a type of low-level programming language which consists of sequences of zeros and ones. So that is the binary digits that the computer understands. Okay, so the computer understands something being on or something being off. An on is represented as a 1, and an off is represented as a 0. Okay. Okay. Now, based on the instruction we want to tell the computer, we might write a sequence of zeros and ones. For example, we might write 1 0 1 0 1 1 0 0 1 0 1 0 1 0 1. Okay, and this might tell the computer to do some specific instruction. Okay, now we need to learn different machine languages for different manufacturers or different computers. Okay, so for example, if you have a Dell machine, the machine language on the Dell will be entirely different from the machine language on the HP or on the Lenovo, because they are built by 3 different companies. Dell builds their own, HP builds their own, and Lenovo may build its own. Okay, so machine language is a bit complex because of the zeros and ones. You have to memorize what the zeros and ones represent and what they mean. Okay, and but the sweet thing about it is that because you write directly to the components, you know, or it is faster. No need for translation. Once you write them and you run them, they run. No need for any translation whatsoever. Okay, so it's very, very fast and it's simpler to use. Now, because of the 0 and 1 wahala or the problems with 0 and 1, another programming language was designed to make it easier for people to write computer programs. And that programming language is what we call assembly language. Okay, so assembly language, instead of using directly zeros and ones, we used mnemonic code like move, add, subtract or sub, multiply, load, and all those kinds of instructions. Now, this one too is okay. Okay, this one too is okay. This one is probably okay. It's better than memorizing zeros and ones, but it is also still a little technical. And there was a problem, because the key problem here is that because you are not writing in zeros and ones, but writing in English, you will need to translate from maybe add back to 0 1 0 1 0 1 1 0. Okay, you need a way to move from here to here and then back whenever you are doing the reverse. Okay, so to sort that problem, they built a program called the assembler. The assembler is a translator. Okay, so the assembler is a translator which is responsible for translating the assembly language code into a machine language code. So you will write in English, and then the assembler will translate the English into zeros and ones for the machine. Remember, the English is for you, and then the 0 and 1 is for the machine. Okay, so that was what made it easier to use. But apart from that, it's still the same thing. That's why we call it a low-level programming language. Okay. Now, another key thing is that because low-level programming languages were hard, okay, and difficult to comprehend and teach, or yet still understand for beginners, they built a programming language which is easier for humans to read and understand. Okay, read, write, and understand. Okay, so that programming language, or those programming languages, are referred to are what we refer to as high-level programming languages. Okay, they are written using common English words or phrases or expressions, and they look pretty much like the English that we read and write all the time. Okay, so we have languages like Fortran, Pascal, Lisp, C++, COBOL, C, Java, Objective-C, Cocoa, Elang, and so many other programming languages. Now, the catch here too is that all of these programming languages, yeah, they are easy to understand. They are much more safer and more friendlier to human beings. But the problem with them is that they are written, or they are written in English or in human readable form. They are not written in zeros and ones. So they need still to be translated from the English that we write them from, or we write them with, into a form which is easier for the machine to work with. Okay, so we'll come to that. But before we come to that, we also want to find out why we refer to them as high-level programming languages. We refer to them as high-level because of certain features. Number one, they need a level of abstraction. When we say abstraction, we are simply referring to the ability or the feature of a programming language to hide the details of how things are implemented. For example, when you are a programmer and you begin to learn Java, you don't have to, or you don't worry yourself with the details of how the machine, whether the machine is a Dell or HP or Lenovo, or it's a MacBook or whatever it is. All you need to understand is how to write your Java. Okay? You are only concerned about your Java, and the machine takes care of all the Java, takes care of all of the rest of the things. Okay, you don't even know how much memory is on the machine, whether there's enough memory or not. those things are kept away from you because the programming language takes care of those things. That's what we call abstraction, okay, to hide the details of how the implementation is, okay? Then, secondly, and more importantly, high-level programming languages must be readable. For it to be high level, it must be readable, okay? So we can actually understand the syntax. The syntax means rules, okay? So the rules we use to write Java or C or C++ or any of those high-level programming languages, they are much, much more simpler than the rules you use to write an assembly language code. Assembly language code is quite technical and very can be a handful, okay, if you don't or you're not familiar with it, okay? Next thing too is that you can run or write high-level programming languages on different platforms or different machines, but you can't do the same with low-level like assembly or machine language, okay? With machine language or assembly language, each machine has its own assembly language. You cannot go and take Dell's assembly language and come and write it on Apple or write it on maybe Lenovo's assembly machine. No, you have to use Lenovo's machine language for Lenovo, Dell for Dell. But if you install Java, it doesn't matter whether you install on Dell or Lenovo, it will run. You don't need a different Java for different machines. Okay, that's what we mean by portability. And by that, because of these features, it helps you, the programmer, to build faster, okay, to be more productive. And then other features include what? Modularity. You can break things down into specific groups, data structures. It has complex or simple structures for managing data, and then has a user interface. User interface means that it has a nice screen, unlike machine language, which may not necessarily have a nice screen, or assembly language, which also may not have a nice screen. I'll pause over here. Is there any question so far?
Oh, sir.
Okay. Let me check the chats. Okay. So far, nothing yet. Okay. Like I said, if you have any question, feel free to post it or to raise your hand so that we can address it. Okay. Okay, so continuing, like I said earlier, because this one too is written in English and not in zeros and ones, you need to translate it. Okay. Now, the program the programmer, writes is called source code. When you, programmer, write code or write a program, we call it the source code. Okay. Now, when the program is translated, okay, into machine code, the translated code is called binary or object code. Okay, binary or object code. Some books prefer to also use the term target code. Okay, but it's not really common. The most common terms are object and binary code. So when they translate your code, your source code will be translated into a binary or object code. Mr. Henry Ganser. Mr. Henry
Yes, sir.
Ganser.
Good evening,
Yeah.
sir.
Yes,
Yes, sir.
evening.
Good evening, sir.
Okay, please go on.
Please, I wanted to ask a question. Since you are talking about the coding,
Yes.
I wanted to know if the processor of the laptop or desktop, whatever, can be changed. Let's say you have Intel Pentium, you want to change it to, let's say, Intel Iris or i7 or any other thing.
No.
Okay.
Hello.
Yes, sir, I'm here.
Did you hear me?
Yeah, I heard no. I
Yes,
wanted to.
no.
Yeah,
Yes.
I heard no. I wanted to know why.
Oh, that's, for example, if the machine, for example, if maybe I buy a MacBook 2015 or MacBook maybe 2022, okay? It is built using maybe an Intel dual core, maybe i5 processor, okay? Now, the board, and
Okay.
even, have you seen a processor before? You've seen one, right?
Yeah, I've seen some.
When you
Yeah,
pick it
yeah.
up and you
It's
turn
embedded
the
on the
back,
board.
sorry.
It's embedded on the board.
Oh, no. You can take it out. When you pick it up and you pull it out of the board and you hold it, do you see that it has some of them have pins underneath it?
Yes.
So
Yeah, they have pins.
the pins have been arranged in a specific way, and you'll be surprised.
Okay.
It is only the same type. For example, your i5 processor can get spoiled, and maybe you take it out of the board. You cannot put an i7 on the board again. You have to put the same class and type of processor onto the board, else it will not work.
Okay.
If you try
Thank you,
to
sir.
force a different processor, the pins will break, or it will not even turn on, or it will reject the processor outright. Okay, that's how they have been built.
Okay. Thank you, sir.
You're welcome. Okay. So there are two main classes of language translators for high-level programming languages. We have a class of translators called interpreters and a second class called compilers. Okay, so these are the two main types of translators we use to translate high-level programming languages from source code to binary code or object code. Okay, let's discuss them. The first one we call compilers. Okay, they are not in any order actually. Now, compiler is a language translator which will translate a program written in source code to another program written in the target language or the object code. Okay, so for example, if you write your Java, okay, and you run the Java, what the compiler does is to take your Java code and translates it entirely into something else. Okay, so the file that you see from the Java code, you will not see the Java again, but you see it in maybe zeros and ones, or you see it in another form, which is no longer in Java, but the form which it is in is either a target language form or an object code form or an executable form. Okay, so compilers take the entire program and translate it completely. Okay, examples of programs that can, or programming languages which are compiled include what? Ada. We have Algo. Okay, this programming language, the first one, Ada over here, was named after Ada Lovelace. Okay, and then we have Algo, we have Fortran, we have C++, we have C#, Objective-C, we have Swift, we have D, we have COBOL, we have Java, we have BASIC, we have Clio, we have Eiffel, we have Crystal, F#, Elan. In fact, we have so many of them. Okay. Hey, what's going on? I can see people. Is that phone numbers? Hello?
No, sir, that's the index numbers.
Okay.
They are index numbers.
So they are claiming they are posting their attendance in the group so that you mark them.
Oh, really?
Yes, sir.
I don't know who gave them that set of instructions to them.
Yikes. Okay. Take your time. Oh, is that how the other lecturers did their attendance?
No, the course
Why
rep.
don't you communicate with the course rep?
Okay, we can
was
do a better attendance. I don't think I can go to, I don't think I can walk through this list one by one and then give you attendance. So what will happen is that we can do attendance. We can create a Google form, okay, and then do an attendance with the Google form. Okay, that's very easy. You click the link, you go and just mark your attendance, and then it will be very easier than posting it here for the course rep to look through one by one. Come on. That's
okay, sir. Thank you,
there
sir.
are over 100 of you. Okay, so I thought it was even a question. I wanted to come and answer it. I didn't know that they were posting index numbers. Okay, so let's quickly go to interpreters. I know you are tired, so you need to sleep. You need to sleep very quickly. So interpreters, on the other hand, are also another type of language translators. Now, how do they work? For an interpreter, it will take the code or the program you have written and directly execute it. Okay, so an interpreter will take the program you have written. For example, if you write in maybe, what's an example? Python. So Python is interpreter. So if you take the Python and you write in your Python, instead of translating the Python, it will take the Python code and work it. I don't know how to put it another way, and run it so that the Python code will run directly from something called a virtual machine. Okay, I believe most of you have heard about this term. Okay, so a virtual machine or VM. Okay, so programming languages that do this kind of thing, when you install the interpreter is a virtual machine. So when you write your code, instead of translating the code for the hardware, the virtual machine will rather take the code and pretend as if it is hardware, and then it will run the code itself without translating it for the hardware of your computer. Okay, so it will pretend as if it is a machine on its own and then run the code inside. Okay, we call these types of translation an interpreted programming languages or programming language. Okay, so it's also a type of translator, but it doesn't do the translation like the way traditionally we do the translation. Okay, sometimes we simply refer to it as a line by line or statement by statement translator. What it means is that it takes the code and then tries to work or run the code line by line. Examples are APL, okay, APL, okay, BASIC, LIPS. So BASIC, you've seen BASIC in the compilers and BASIC in the interpreters, okay? So we have BASIC, the old one, and then BASIC, the one that is owned by Microsoft, okay? So Microsoft has Microsoft BASIC, okay? So please take note of that. And then LIPS, and then GNU, Octave, Mathematica, MATLAB, JavaScript, Lava, GameMaker, Perl, TK Solver, Euphoria, Mosaic, and so many other programming languages. Okay, so most of these programming languages are very simple to learn. Some of them are a bit more up there, but you can see that interpreted programming languages they look more simpler to learn. Okay, so please take note of that. Now, I have a table here containing the key differences. Number one, we learned that compilers translate the whole program, whilst interpreters translate line by line or statement by statement. Compilers appear to take longer but are faster, but interpreters appear to be slower, to appear to be fast, but they are actually slow overall. Okay, then compilers can get you an intermediate form, but interpreters cannot generate an intermediate form. Then compilers report back on the error after translating the entire thing. But for an interpreter, it will keep translating line by line until it encounters an error. At the place where the error is, it will stop. It will not continue. Okay? So for example, if I make a mistake on line 2, I have 10 lines of code. I make a mistake on line 2. For the compiler, it will try and translate all the 10 and then tell you that, oh, there's an error. And then you will now figure out where the error is. Okay? But for the interpreter, it will translate line 1. Then when it gets to line 2, it notes that, oh, there's a problem on line 2. It will stop at line 2. It will not continue to line 3 or line 4. No. To stop at line 2. Wait for you to fix it before continuing. And so we have some examples down here. And then finally, but not the least, we have scripting programming languages. So scripting programming languages are sequence of programming languages which run inside others. So I gave an example earlier, like for example, if you have a programming language like HTML, I don't know if any of us have heard about HTML. It's a programming language used to build web pages. Now, you can write cascading style sheets inside HTML. You can also write JavaScript, okay, inside HTML. You can also write Perl inside HTML. In fact, you can write PHP inside HTML. You can also write Python, okay, inside HTML. In fact, you can write something called SQL inside HTML. And so all of these ecosystem of languages are referred to as scripting because they are scripts. They are written with very simple commands. They are easy to write one inside the other, but you can't write maybe C++ inside Java. It will not work, okay? But with scripting languages, you can do something like this. You can write one language inside another programming language. So this is the end of the introduction and the first lecture. Please, I need to do some announcements, but before then, if there's any questions, and then we will deal with the questions, and then we will be out of here. Any questions? Any questions? Yes. Any questions?
No, sir.
No, sir.
Okay. Everybody understands everything?
Please, I raise my hand.
Okay.
Good evening,
So we
sir.
go from Isaac.
Good evening, sir.
Yes, sir.
Please, now I want to know, do we have any device that serves as input and at the same time output device?
Oh, yeah. So don't you use a phone? Do you use a phone?
Yes, please.
So have you not noticed that the screen of the phone, you can see, you can see the output of the phone, and the same screen too, you can use it to enter information into the phone.
Please, is modem part?
Oh, calm down. I'm asking you a question. Have you not seen that the screen of the phone is a touch screen, right? So you can use it to see the information which is out, and you can use it to enter information which is in. Do you see?
Yes, please.
So it's possible. It's possible. And now you're asking whether a modem is input and output. No, a modem is actually a communication device. It doesn't show you anything. It's just communication. Okay. Hello.
Sir, I mean, copy, sir.
Okay. So, Mr. Otabel.
Hello, sir.
Yes, sir.
Sir, please, I wanted to know whether the HTML is a website or it also have an application software.
Oh, HTML is a programming language. I did say it when I was mentioning. I just said HTML is a programming language. Look, oh, it's not included here. Okay, it's a programming language. It's a program. It's not a website. It is used to write websites. Okay, and it's not an application software.
Oh, okay.
It's a programming language.
Understood, sir.
Okay. Nathaniel.
Yes, sir. Please,
Yes, sir.
I wanted to ask if a balance scale falls under computer.
A what? Hello?
Hello, sir. Yeah.
I didn't get your question. Hello?
I was asking if a balance scale falls under a mechanical computer.
What does it look like? What was it used for?
They have some pendants that they put on one side, and they put the, how do you call it, the thing they are measuring.
Okay, so let's do a criteria check. Does it allow you to enter some information?
So,
or does it collect some information?
On one side, you can put
inputs. Okay, so correct. So input is correct. Does it process that information using some instructions?
One out of a load on one.
Pardon? Hello?
Yeah.
Yes, I'm asking a question. Does it process that information?
Yes.
Okay, and then does it give out some output?
Yes.
Okay, so it's a mechanical computer. Okay. Okay. Okay, I think he's gone. God's way.
Yeah, sir. With the interpreters and the compilers.
Okay.
Yeah, so you made us understand that, I mean, the language the computer understands, that's the zeros and one, that's the binary code.
Yes.
So which means that, so it means both the interpreters and the compiler, both at the end of the day, convert the code to the binary code. But
not quite.
But with the interpreter, it does that at runtime. Because the difference we have over here, it means that with the interpreter, I mean, it translates the code to the the machine code, like line by line at runtime. But with the compiler, it does all at once before it executes.
Yes.
Yeah, the reason I'm asking that is if what the computer understands is the binary code, which is the zeros and one, then it means that at the end of the day, we should have, the binary code for the computer to be able to run it.
Okay. So that's why. Have you seen this thing over here? This thing here. Target language. Hello?
Yeah.
So target language or object code or executable may not necessarily be binary code. Are you with me?
Yes, sir.
Okay. So yes, computers understand binary only, but the translator or the compiler or the interpreter may leave the code in another form. And then another program will pick that code and now convert that code into binary. Okay, so a typical example is Java. Okay, so Java is first compiled. Okay, so when you compile Java, you get something called bytecode. Okay, now bytecode is not zeros and ones. Okay, you'll be surprised when you convert Java, and the first step you get bytecode. It's not zeros and ones. It is not binary code. You would rather the computer rather pick the bytecode and now go further and translate it before it gets binary code. Okay, so it's not all the time. It's not a monolithic something. It's not all the time. Sometimes we leave it in, and that's why this table says compilers can leave the code in an intermediate form. Okay, they can generate something called intermediate code. Intermediate means that in the middle. The thing is not the thing you wrote, but it is not the final product. Okay? Hello?
Yeah, I can hear you, sir.
Okay, do you understand me?
Yeah.
Have I answered your question?
Yeah, but I mean, so but at the end of the day, what the computer actually runs is the binary code.
Yes. At the end of the day, some some program must make sure that the computer can run or the hardware can understand what you have written. Okay.
Oh.
Yeah.
All right.
Emmanuel, is it Emmanuel Tete?
Yes, sir.
Yes, you are next. Yeah.
Sir, please, on the compilers and interpreters,
yes,
are they embedded in programming languages like Python, or they are run separately?
Oh, they are. In fact, if you want to run Python, you will go to Python's website. Okay. When you get to Python's website, you will download Python. Okay. Now, the moment you download Python and install Python, you have installed the interpreter for Python. Do you get that?
Yes, sir.
Okay. So the moment you download Java and install Java, you have installed the interpreter for Java.
Yes, sir.
The compiler for Java. Sorry. Okay.
Yes, sir.
When you go to the website of the programming language, they will tell you whether the language is compiled or interpreted. It's there. Every information is there on their website. Okay.
Thank you, sir.
God's way, put your hand down, okay? And then Emmanuel, you can put your hand down. Evans, you are next. Evans. Hey, who is that?
Sir, please, good evening. Yeah, sir, please, talking about the virtual machine. Most times you see them running on the 64 bytes. Is it possible for them to run on the 32 as well from the old virtual box?
So Buckman, please, you're muted.
Hello, can you hear me?
Yes, we can.
Yes, we can.
Oh, sorry. I don't know how I got muted. Wow. Okay. Sam, I didn't hear anything you said though. Okay, Mr. Sam, please. Mr. Evans, I didn't hear anything you said. Mr. Sam, please go on.
So I was going to ask that now, given the fact that we're talking about the high-level languages and then rely on the interpreters and compiler, how do you decide in the instance where you use like a C plus versus an interpreter like Python? How do you decide when to use any in the critical application? Maybe you are writing an application. How do you decide when to put which?
Oh, you unfortunately you do not decide. For example, if you decide to write your app in Java, okay, the moment you install Java, you've installed the Java compiler. There's no Java there's the compiler comes with the compiler and the virtual machine together. Okay, so when you install it, it comes together. For example, if you in the future, I learned that you learning C++. So if you now move towards learning C++ and you go and then you install the C++ compiler, it comes as a compiler. It doesn't, there's no interpreter and compiler. It's just one. It comes one like that. Is that the answer? Or sorry, have I answered your question?
Yeah, okay. I think so.
So the programming language determines the kind of tool you get.
Yeah. Okay. So let's say, for instance, you are maybe using something like a Visual Studio to do your write-ups.
Okay.
Yeah. So you know that in Visual Studio, sometimes when you are rendering, it does the individual line checking and then write off your errors for you. And then in Visual Studio, you need to install the various language models individually. So that which was why I was asking the first time?
Okay. Those things are tools in the programming languages. So, tools in the text editors. Okay, so the Visual Studio Sam is talking about, to those who don't know what it is a tool. It's a text editor. It's called Visual Studio Code, VS Code, right? Is that the one, or you're talking about Visual Studio for VB?
No, that's it.
Okay, so VS Code has a tool called a debugger. Okay, so it comes as a plugin. Like in VS Code, you add add-ons or plugins to make the text editor more to add more features. Okay. So for example, if you want the text editor to be checking your code for you and to be telling you where you have errors, you just add the add-on, so that as you are writing, even though you are writing C++, the text editor itself can check your C++ line by line and tell you where the error is. Okay, the fact that the text editor is doing that doesn't mean the C++ has changed from being compiled. No.
Okay.
Every time you click on run, it will still do the compilation, whether it is checking line by line or not. The compiler itself, every time you click run, it will do compilation before it will continue. Okay, so those things are features you can add. We have something called annotation. We have text completion. We have so many features you can add. Or these days they come with programming languages, so it makes it easier for people to use the particular maybe app. But the compiler or the interpreter, they work the way I've described. Okay.
So is this course going to cover those to that level?
No, this course will cover structured programming. So we'll teach you structured program design. So we will not pick a programming language, but we will teach you how to write the logic for structured programming. Next week, God willing, when we meet on Saturday morning, we are going to learn what structured programming is and how to piece together programs that are structured programs. Okay. So you learn variables, you learn those basic things, variables, data types, constants, logic, control structures, all those things. Those are the building blocks you need before you even start learning C++. If you don't learn this one, it will be difficult to learn anything substantive in programming.
Right.
Mr. Felix. So last two.
Hello, sir.
Yes.
Good evening.
Good evening, Mr. Felix.
Okay, so you were saying there are some languages that we used to write websites.
Yes.
Website. So, sir, I wanted to ask, third parties app like WordPress and other websites where you can use to create a website without you inputting a computer language. How about that one too?
Yes, those are not programming language. We call them CMS systems.
Okay.
Did you hear me?
Yes, sir.
We call them CMS systems. So what they do is that they have it's a framework packaged into an engine of sort. You click your way into creating the website, right?
Yes, sir.
Yes. We teach that. There's a course I've taught some time ago that we teach that. It's called web authoring. Okay. So we use CMS systems like Joomla or WordPress or Wix or any of those tools. And then what happens is that those tools already have the frameworks and then the code and all those things. So when you click anything you click, they copy the code or they put the code or activate the code within the block. Okay. So it's also a program that can create websites, but it's not a programming language.
Okay, sir.
Okay. Mr. Paul, thank you for your patience.
Hello, sir.
Yes, sir.
Sir, please, with the coding and the computer programming thing, do we need a specific laptop to do all that?
Yeah.
Like
These days, you can actually write your programs from your phone. Okay. There are websites which have online compilers or interpreters, which you can use to write your, let me see if I can, let me see. So I want to show you a tool like that. Okay.
It's a good thing.
There's a tool called, what's it called? Programize. Okay. I don't know what is programize.com. Okay, so this is it. Okay. So these days, you need a web. The ideal thing is to get maybe how do you call it? To get a laptop and then run the thing from a laptop and all those things. But if you're also not with a laptop, it doesn't mean you cannot do programming. Okay, so these websites like this one, right? You see all of these things. They are compilers and
thank you.
tools. So you can use some of them. So for example, if I click on this one, okay, I'll show you. So you see, you can write code here. You can write code here, like you were writing on your phone. Sorry, you were writing on your how do you call that thing? Laptop. And then when you click on run, notice that it will run the code for you. Okay, you see that? Do you see the outcome? Hello, Bernard, over here in the output window.
Yeah.
Hello. Hello.
Yes, please.
Yes, sir, we can hear you. We can hear you.
Okay, so you see that there are tools like these ones, so that if you don't have a laptop, you can run from them. But the only disadvantage is that you cannot save things here. Okay, you cannot save things here. You have to copy them and paste them somewhere if you want to save that code. Okay, so it leads me back to my LMS. So I want to quickly ask that. Yikes. Okay, so I want to quickly ask that we try as much as possible to visit the page. Now, when you visit the page, for example, so at the end of every week, they will change the video. Okay, they will change the video. Sorry. I think they will change this. This is the last video from 2025, so they'll change it, and then very soon you will see March 2026. Okay. Then we have our course description on the page. We have announcements. We have introduction. So you introduce yourself. Okay, it's a discussion. So all you need to do is to click on the discussion, and then you see Collins Afrifa. He introduced himself. Okay, it's a simple question I ask. So you introduce yourself, and then you tell us your main expectations. Okay, so all you have to do is that when you want to reply to this at your end, you just click reply, and then you get a box, you type your information in there, and then you just go. Okay, you just click post and to post. Okay, now I want to show you the next thing. The next thing is that also over here we have our course manual. Our course manual is also over here. When you click on it, you can download it. Okay, but for now, I will change some of the things on the course manual so that it will be reflective of the dates. Okay, so please hold on for that. And then our lecture slide 1, session 1. Okay, so here too, there's a small assessment I want you to go and do. So currently, you have 2 attempts. Each person has 2 attempts, and you need 7 minutes for each attempt. Okay, so you can answer one, or you can use all 2, right? At every instance, every time you click on the question, or every time you click on start, it will change the questions within the thing. So I want to show you one example. Okay, so for example, which type of memory is volatile? And then you click on one of them. Maybe let's say if you click on this one, and then if you don't want, you click on clear. Okay, did you see that? If you don't want, you click on clear. Okay, and then you go, and then you can see that you will be seeing the time as you are also working so that you know her number of times. And you see that the question number as well. Okay. If you think that you don't know the answer, but you want to go and come back, you click on flag. So you see on the left hand side, there's a flag question as well. Okay. Okay. So let me go back to the course. Yeah. So session unit 1 is opened. Then we go to unit 2. Unit 2, I have not opened the stuff yet, so you'll not see all the stuff. I want to correct and change a few things before you can see the stuff. So we'll do 8 units. Okay, 8 units, and at some point in time we'll do 8 units with different sessions, session 1, session 2, and those kinds of things. Okay. Any questions? If there are no questions, then I'll call it an evening, and then I'll have us go, and then we come back next week. Please, everybody should attempt the questions. Okay. By tomorrow, I'll remove all the old entries, and only the new entries will be in the system. And so you can start attempting it tomorrow. Okay.
Okay.
Okay, sir. Thank you, sir.
Right.
Yeah.
So we're grateful for your time, and
thank you too for
appreciate
making time for me. Okay.
Yeah. Thank you.
Tomorrow, next week, Saturday morning. Okay.
7 a.m.
7 a.m.
So
Thank
please,
you.
should you subscribe to the forum at the same time?
Subscribe to what?
The forum.
Which forum?
There's a forum. There's a forum when you open the.
It's just a small discussion. It's called a discussion forum. You go there to to introduce yourself and to tell us your course. There's a question. Kindly introduce yourself and briefly share your expectations. If you want to subscribe, that's fine by you. It means everybody's message, you will see it. That's what subscribe means. Okay. When everybody responds, you will see it. But all you need to do is just to answer yours, and then you go. Okay.
Okay, sir. Thank you, sir.
Okay, you're welcome. Thank you too. Bye-bye.
Bye. Good night, sir.
Good night. Yeah, thank you.
Sound sleep, sir.
Thank you.
Good night, sir.
Class rep, do you have something for us, sir? Don't preach you.
Rep, no,
We're gonna cry.